Right, let's get started. So this is lecture 4. Okay, so before that, this is SeungryongKim. So this is lecture 4 of this advanced computer vision class. So before that, we discussed the visual perception model, object detection or segmentation, right? So today we will move to generative model. I mean the generative model, especially GAN, generative audio-visual network, and we will see some kind of technique to interpret your generative model. Okay, so before starting, the generative audio network GAN has recently achieved impressive results for many real-world applications and many GAN variants. Okay, so this is the original GAN in 2015, 14, right? After that, there was the impressive progress of the image generation. For example, DC GAN, PG GAN, style GAN. We will talk about style GAN today, and big GAN, style GAN, version 2 or the style GAN ADA, right? And many GAN variants have emerged with improved in sample quality and training stability. And last year, it's not last year, in 2020, there was another paradigm, neural radius field, NERD, right? So we will talk about this one a little bit. Last year, there was another paradigm, VQVAE. It's not a GAN anymore, but it's another generative model. So it was the Dali paper by OpenAI. So it was another generative model. And more recently, this year, there was another boom about diffusion model. Diffusion model is another kind of generative model, right? So some kinds of paper argue that diffusion model fit the GAN model in terms of the image generation quality or the stability, but there is an open question. But anyway, the progress for the image generation have emerged more and more. Okay, so today we will see what is generative model and focusing on generative audio network GAN. Of course, it's not a state of art anymore, but the understanding generative audio network is I think the good starting point to understand the generative model. So we will start with the GAN, and we will see. Okay, so we will start with original GAN paper, and we will move to the recent advanced GAN model, and we will see some kind of stunt paper and move to the another topic, interpreting GAN. Okay. Of course, there are so many kinds of relevant topics. For example, autoregressive model, image-to-image translation, style transfer, or the image manipulation, something like this. But today we will not cover many others. So we will just focusing on what is GAN or what is generative model. So what is generative model? So question is there anyone who first heard about GAN or the generative model? 자, 여러분 이제 우리 오늘은 GAN이라고 하는 걸 배울 거고, Generative Model이라고 하는 거에 대해서 좀 오늘 그리고 다음 주까지 아마 얘기를 할 것 같아요, 그렇죠? 자, 뭐 시작하기 앞서서 뭐 GAN이라고 하는 걸 처음 들어보는 사람 혹시 있나요? 또는 Generative Model을 처음 들어보는 사람? Even though you are now working in the computer vision field, you may already heard about what is GAN, right? And what generative audio network is, right? To start to understand the artificial intelligence, right? So today we will briefly discuss generative model and briefly mention what is the generative audio network and move to the advanced text. Okay. So to understand generative model, we have to discuss what is discriminating model and what is generative model. So formally, discriminating model is to estimate P probability of Y given X. In this case, X is input and Y is output. So this is the kinds of supervised learning. So the goal of this kinds of discriminating model is to find out mapping function between the input X and Y, output Y. So in testing time, we can just generate output or estimate the label Y given X input. So this is discriminating model. Then, what is generative model? Generative model aims to estimate P of X, probability of the input X, or joint probability of input X and Y. Joint probability of input X and output Y. So why we need this kind of probability? So if we already know the real probability of the real data, our data, then we can generate real looking like data starting from the random noise. So in other words, even though these generated images or the generated data is not real, but if we can make real looking like data, we can do many things. So this is one of the objective of the generative model. Or if we have joint probability of the X and Y, then we can generate X given random seed or output Y class, right? Class Y. So this is kind of class conditional or the class conditional image generation or the class conditional sample generation. Or we can make a training sample X and Y from the random one. This is kinds of generative model. So in many cases, this generative model is trained in a unsupervised learning paradigm. Right. So I'd like to show you some example. Okay. Let's suppose that we have an input data X and output data, the output class label, right? Like that. So it's very simple binary classification problem. So let's think about the discriminating model first. So the aims of discriminating model is to find out Y given X, right? So to understand this, we have to estimate P of Y given X. So we can just make this kind of table. So this is the conditional probability table, right? Then if we have this kind of one, we can just say that, okay, so probability Y is equal to 0 is that given X is equal to 0.1 is that 0.33, right? Y from this here, right? Then we can say that probability of the Y is equal to 1 is 33%. This is a discriminating model. What about generative model? What about generative model? We can do many things, but today we will just focusing on learning probability of the input data X. So how can we make this kind of table? We can just count number of sample. So X is equal to 0.1 case, there is a 2, right? And if X is equal to 0.1, there are 3 kinds of case here and here and here. So we can easily make a P of X. Then at testing time, we want to generate the sample that similar to this real data. Then how can you do that? There are many kinds of technique, but first of all, we can just generate interval depending on this one. So for example, okay, here's 0 to 1, and here's 0.2, 0.5, 0.6, something like this. So if we randomly sample the values from 0 to 1, okay, for example, we sampled the random values from here, then we can say we can generate x as a 0, 0, or we sample the values from here, then our output, I mean x is going to be 0, 1, or like this. By doing this, our generative model can produce the x which is not real, but which is similar to the real value. I mean the real vectors or the real samples or real data. So it means that the output sample resembles the real data distribution. So this is generative model. So let's move to the image generation model. In computer vision field and the computer vision generative model or the image generative model. So in computer vision, we have so many training images. So let's suppose that this is the data coming from data P data X, real data distribution of the real data distribution of the X. Right? So the goal of the generative model in computer vision, given training set, generate the new samples from the same distribution. Same distribution means same distribution to the real data distribution, and we generate the model P model X, P model of X, then sample from this this P model distribution and generate the images that cannot be discredited from real data, real images. So we have two objectives: learn P model of X that well approximate P data of X, and then sampling new X from the P model X. So this is the objective of the generative model. 그렇죠? 앞에 너무 쉬운 얘기들이죠. 그 generative 모델이 왜 필요하느냐? 결국에 우리가 가진 리얼 데이터를 모방하고 싶은, 결국에 우리가 어떤 모델이 리얼 데이터의 디스트리뷰션을 모방하고 싶은 거죠. 그리고 그 모델을 모방했다면 그 모델로부터 우리가 새로운 X를 샘플링해서 쓰고 싶은 태스크가 너무 많기 때문이죠. 사실. 그렇죠? But okay. So this kind of technique can be formulated as a density estimation problem. So I mean, how to model real data distribution. So there are two kinds of technique: explicit density estimation, implicit density estimation. Explicitly density estimation explicitly defined as solve for the P model X. In implicit density estimation, learn a model that can sample from the P model X without explicitly defining it. So first of all, modeling real data distribution, I mean the modeling image data distribution, it's going to be maybe impossible, or it's going to be really challenging, right? So because the image data distribution, I mean the image data manifold is going to be really complex, right? Complexing, so it may be impossible. So implicit density estimation is the more feasible direction to model your image data. So again, today's topic is one of the methods for the implicit density estimation. So when you think of the taxonomy of the generative model, so there are two kinds of categories: the explicit density estimation, implicit density estimation, and there are so many kinds of the explicit density estimation method. For example, pixel RNN, CNN, or the variation autoencoder, or autoregressive model, something like this. But one of the popular implicit density estimation method is GAN. So today's topic. So then what is GAN? What is GAN? Oh, by the way, the question is there anyone who first heard about GAN or the generative adversarial network? 자, 여러분 이제 조금 이제 앞에 뭐 서론 얘기를 했고 이제 간에 대해서 좀 얘기를 할 건데 사실 간 페이퍼를 완전 처음 들어보는 사람이 혹시 있을까요? 이게 조금 너무 디테일로 가면 너무 오래 걸릴 것 같아서 제가 많이 스킵하려고 하는데 오케이. Okay, one. Any others? Any others? Or how much do you know about GAN? Other student. 자, 다른 친구들 혹시 뭐 간에 대해서 얼마큼 알죠? 그냥 뭐 대충 다 알죠? 뭐 이렇게 간의 the objective function of GAN or the how to train this min-max player game, something like this, right? You already know. Maybe. Please give me a comment or 혹시 다른 친구들 좀 의견 좀 줄 수 있나요? 이상생 How much? 오케이. 오케이. 대부분이 아마 많이 알 것 같아요. overall concept, 그렇죠? I know the overall concept. Yes. Okay. So today I will briefly recap the GAN. But if you're the first time to study the GAN, please watch the GAN tutorial. There are so many kinds of GAN tutorial in YouTube or the other material. So please recap what is GAN. Okay. 뭐 그렇죠? 여러분들 많이 알고 있네요. 자, okay. There was one question. I saw distribution P data is not depend on X notation to represent the GD distribution P data. However, would the GAN paper use the notation P data? Could you explain the reason? Okay, the very good question. P data is dependent on X. P data is dependent on X. Okay, so let me explain why. So let's think of the images, very simple images. For example, 2 to 4 by 2 to 4 by 3. 2 by 3. Okay, and let's assume that each pixel represent 8 bit, so from 0 to 255. Okay. The question is, in this case, how many kinds of images can emerge in this case? 준성? So 2 to 4 by 2, 2 by 3, and each pixel can have the value 0 to 255, right? In this case, how many kinds of images can possible? Or other student? 뭐예요? 우리가 24 by 24에 256의 제곱에 3의 3승 24, 24, 256의 3승 조금 더 생각해 봅시다, 여러분. 자, 우리가 그냥 24 by 24 by 3이라고 하는 이미지가 각각의 픽셀은 0에서 255까지 값을 받을 수 있다고 생각을 해보면 그 이미지가 가질 수 있는 경우의 수는 아니, 이거 내가 잘못했나? 이거죠. 24 이거죠. 그렇죠? 아닌가? 맞죠? 2 to 4 by 2 to 4 by 3 over 255. 그렇죠? Whole possible images. Right? 그렇죠? 맞죠? 아닌가? 맞죠? 맞지 않나? 맞죠? So, in this case, probability means 오케이. 미과 지수가 그치. 맞아. 반대지, 반대. 255에 anyway, it's infinitely many cases, right? Infinitely many cases. Like this. Then, so when you think of the whole possible images, it's going to be 0 to 255 over 5 to 2 to 4 by 2 to 3. So in many cases. So the real data distribution maybe looks like this. It's going to be really sparse. So real possible image is going to be the very, very sparsely located on this axis, right? So p data x means this kind of probability, right? So to mention p data x, we have to think of what is the data, what is the probability of the current x? What is the probability current x? Okay. So 그 한국말로 한번 더 설명하면 무슨 얘기냐면은 결국에 0부터 25에 244, 243의 어떤 거의 인피니트 매니 kinds of 이미지들 중에 진짜 리얼 이미지들이 나올 수 있는 어떤 확률 분포를 생각해 보면 뭐 정말 이렇게 스팔스한 이 확률 분포가 될 거예요. 그렇죠? 그 확률 분포를 우리가 얘기를 하는 게 결국에 p 데이터 x를 말하는 거고, 그렇죠? 그렇기 때문에 우리 지금 누가 물어봤더라? 준상쌤 물었던 것처럼 결국에 x의 디펜던시가 있죠, 그렇죠? 결국에 x의 디펜던시가 뭐 예를 들어서 x가 여기 있다. x가 그 중에 하나겠죠? one of the possible images, 그렇죠? x가 하나일 때 그 probability를 말하는 게 결국에 중요한 얘기다 라는 거예요. 그렇죠? 빨리빨리 넘어가려고 하는데 좀 걸리네, 시간이. 조금 해봅시다. 자, so the problem is we want to sample we want to sample from complex high-dimensional training distribution. So and there's no direct way to do this because this is complex and high-dimensional training distribution. So solution is sample from the simple distribution, maybe Gaussian distribution. We can easily sample from random noise, for example, and learn transformation to training distribution. So random noise to the image domain. So what can we use to present this complex transformation? Maybe neural network is going to be solution, right? Why? Neural network has very, very good capacity to represent the mapping function between this random noise to the image space. So let's use the generative network. Then so neural network. But we don't know which sample set maps to which training images, so we can't learn by reconstructing training images. We don't know the mapping between the set and images. The solution is let's use discriminator network to tell whether generator images is within the data distribution or not. So in other words, again, we used two kinds of neural network, generator network and the discriminator network, and train this generator network and discriminator network simultaneously, starting from the random noise. This is the GAN. This is GAN. So training GAN is two-player game. So we have a two network which had two different goals. The discriminator network tried to distinguish between real and fake images or the generated images, and generator network tried to fool the discriminator by generating the real-looking images. Then the training GAN is to formulate the objective function, to solve this controversial objective. So like this. So starting from the random noise that the generator network generate the fake images from the generator, and we have a real image we already have the real images, and discriminator network take both of them and discriminate real or fake, then we train the discriminator with this binary classification problem and train the generator to fool discriminator by generating real looking like images. So how can you do that? We can train jointly in a minimax game, because they have two different objectives. So we can define the objective function looks like this. First of all, the pi theta, the theta t is the discriminator network parameter. Theta g is the generator network parameter. Then we define this kind of loss function. So in fact, this is very, very simple binary classification loss function. This is just like the cross entropy loss, right? Output of discriminator given real data x should be real, right? Output, discriminator output given generated images starting from the Z should be fake data, should be fake class. So by defining this cross entropy loss, the discriminator can train to discriminate this real data and generated data. And in this case, when we minimize this loss function in terms of the generator with theta g, then with this term, we can train the generator to fool discriminator by generating real looking like images. I mean, by making these images similar to the X, we can fool discriminator, or we can minimize this loss function. This is the minimax objective function of the GAN. So in other words, discriminator output likelihood in 0 to 1 of the real images. The first term is that discriminator output for the real data. So by minimizing this term, it's going to be close to 1. Another case, it's going to be 0, right? So this part, discriminator output for the generated fake data g of x is going to be 0 in this case. So discriminator with theta t wants to maximize objective function such that tx is close to the 1, t of g of z generated images is close to 0. So it's close to 0, 1, and 0. And generator with theta g wants to minimize the objective such that t of gz is close to 1. So where discriminator is full into thinking generated gz is real. Gz is real. This is the objective of the GAN training. So question, Junsung, if I remember correctly, the original GAN paper is used notation p data x log t for the part of minimax objective function is the first x is different from the second x. What do you mean? For the part of the minimax objective function is the first x is different from the second x. First x is different from the second x. I didn't follow what you mean. You mean here, this x and this x, right? Maybe, 그렇죠? Yes, right. So two kinds of notation can be used because this is just like p data, or we can just represent p data x. So in this case, x is just a variable, and this x is a random variable. So this x is a real sampled x from this data distribution. So any kind of notation can be used. 그래서 뭐 두 가지 둘 다 사용될 수 있어요. 그렇죠? 상관없죠? So how can we optimize this objective function? So in terms of the discriminator, we can use the gradient offset because this is maximization problem. So this is the first optimization function. And in terms of the generator, we can use the gradient descent because this is a minimization problem. Maximization and minimization problem. That's it. And one more detail is when you think of this generator, when you think of learning generator, it used log 1 minus x. So this loss function is log 1 minus x. So in this case, let's think about 1 minus x, log 1 minus x. Okay, when we draw log 1 minus x, in this case, x means d of gz. 그렇죠? The shape of this loss function looks like this. So there is two kinds of phenomena. When we see here, the x is small. When sample is likely fake, so the output of the discriminator is small enough. We have to learn from it to improve the generator, but gradient in this region is relatively flat. So in this case, this is very, very smoothly changed. So the gradient of this plane. So maybe, so in this case, the slope of the loss function is small. So it's not desirable, right? However, gradient signal dominated by a region where the sample is already good. So here, this sample, the discriminator already discriminator already say that this is a real data, but in this case, this sample generated a large loss gradient, so it's not desirable. So in practice, optimizing this generator objective does not work very well. So in practically many cases, they use another loss function, gradient offset on generator. So rather than optimizing this loss function, they use alternative loss function y is equal to log x. Then it's going to be the maximization problem. So we can use gradient offset technique on this generator. So what is different between previous log 1 minus x and log x? Here. So this is the log 1 minus x graph, and this is negative log x graph, because it's going to be the maximization problem. So negative log x versus log 1 minus x. The loss phenomena is exactly the same, right? As increasing the x-axis, the loss gradient is decreased, right? But in this case, in early training time, I mean, when the sample is likely fake, this kind of loss function, I mean the minus log x, make the large gradient, right? Because it has a larger gradient slope, right? Tangent slope. So in practically choosing objective with a better loss than the same looks like this, half training. So which is the active area of the research? I mean, which is active area of the GAN loss function? Anyway, so by using the the minus log x, minimizing log likelihood of the discriminator being correct, maximizing likelihood of being correct is equal. The same motive of fooling discriminator, but now higher gradient signal for the better sample. I mean at the early stage of training. So it works much better is standard. It is standard in practice. So anyway, so this is the optimization for the GAN. So this is a very popular landscape to understand the GAN. So this blue axis represent discriminator distribution of D, and this green line means generator distribution of PG, and X is a real data distribution, in this case Gaussian, and Z means random noise. I mean, in this case, uniform noise, right? Uniform random variable, and X is a generated sample. And in starting point, our network, starting from the Z to X, our network generate the biased output. Looks like this. First of all, the discriminator D is trying to discriminate the sample from the data. So this blue dot move to the looks like this. Then this gradient of D guide to generator to follow the region that are more likely to be classified as data. So by using this discriminator D as a guidance, this generated distribution move to the real data distribution, and finally alternating discriminator learning and generator learning. Finally, we achieve the consensus between the real data distribution and generated data distribution. Then, in this case, our network can sample the Gaussian-like distribution X from the uniformly defined random noise. 여러분도 아마 많이 봤던 그림일 거고, 너무너무나 중요하면서도 너무너무나 직관적이면서 너무너무 잘 그린 그림이에요. 그렇죠? 그래서 여러분들 한번 이거 조금 한번 리캡한다는 생각으로 그냥 페이퍼 한번 읽어보시면 좋겠고요. So in this case, the decremental output always 0/2. So in this case, decrementer can't discriminate real and fake data anymore. So in this case, we can say that our GAN model is converged. So in this case, real data distribution and the fake data distribution is going to be same in this case. Anyway, this is GAN. So after training, we just used generator to generate the new images, But in recent many paper, there was another attempt to simultaneously use the discriminator at testing time as well. But in general, we just used generator network to generate the fake data from the random noise at testing time. Yeah. Anyway, it's just GAN. And after that, there are so many kinds of advanced GAN model. DC GAN, progressive GAN, scale GAN, giraffe, spade, something like this. So today we will see many kinds of advanced technique. So first of all is the deep convolution GAN, DC GAN, which is a real starting point of the evolution of GAN. So even though the first GAN paper was published in 2014 in New Leaf, right? But at the same time, theoretically, the performance was theoretically GAN was beautiful and GAN is possible to generate any kind of images, but it didn't perform such kinds of high quality image generation due to some kinds of limitation. Right? So after that, there were many papers to overcome this kind of limitation. The DCGAN was one of them. In DCGAN, they wanted formulate, design better network architecture for the generator and discriminator. So formally, they found that generator is subsampling network with a fractional thread convolution. It's going to be the good choice, and discriminator maybe just convolution network. In this GAN, they show some architecture guideline. Replace any pooling layers with a stride commotion in discriminator and fractional stride commotion in generator. Use metonymy in both the generator and discriminator. Remove fully connected hidden layer for the default network. Use value activation in generator for all layers except for the output, and use tangent function. Use leaky value activation in the discriminator for the whole layer. There is no specific reason, but these design choices determined by empirically, but it still contribution, right? Anyway, they found this kind of architecture guideline for the stable GAN training. So after that, many people try to follow these kinds of design choices. So this is the examples of the GAN generator starting from the random noise Z, which is the 100 by 1 vector, and then we upsample this random noise sequentially. The uniform 100-dimensional uniform distribution Z is projected to the small special extend commotion representation using 4 fractional stride commotion. So output is going to be the 4 by 4 by 1024. Then sequentially convolving the convolution 1, 2, 3, 4, we generate the 64 by 64 by 3 images, which is going to be G of Z. 그렇죠? No fully connected where the pooling layers are used in the generator. 이렇게 학습을 했을 때 가장 잘 되더라는 게 이제 DCGAN에서 발표된 거죠. At the time, of course, nowadays this generative sample is very full, right? But at the time, it was the revolution. The samples from the model was looking amazing. This is the indoor images training the indoor data set. This is just the 64 by 64 images, but at the time it was the very impressive result. 그래서 뭐 지금은 우리 사실 뭐가 잘 되라고 하겠지만 이 당시만 해도 이제 이렇게까지 영상이 생성된다는 거는 이제 정말 획기적인 일이었죠. And in this paper, they also show that it is possible to interpolate the latent space, I mean the random noise Z. So they raise a question. We can we can manipulate latent vector as well to manipulate images because they are highly correlated, right? This shows very interesting observation that this is the one of generated images by random noise Z1, and this is another images by another random noise, let's say Z2. Then when we interpolate this Z1 and Z2, for example, like another Z prime is equal to alpha Z1 plus 1 minus alpha Z2, then as bearing the alpha value by through the network, the generator network, we can generate the images looks like this. Interestingly, even though these images, it's not correlated, these images and these images, but these images only correlated in a latent space, but by interpolating latent space, we can manipulate these images looks like this. In other words, we can say two kinds of things. The first one is that this network will learn the mapping function between the Z to the images, and by manipulating Z, we can manipulate the image as well. So they showed very interesting another application, vector arithmetic on the latent space Z for the visual concept. So here's the like that. So this is the generated images by latent vector Z1. So when you see these generated images, they look like smiling woman, and another Z2 generate the neutral woman, and another latent vector Z3 generate the neutral man. So if latent vector Z containing semantic meaning of the generated images, then by manipulating this latent vector set, we can manipulate the semantic understanding of the generated images. In other words, okay, this is smiling woman, so this is a neutral man, and here this is a neutral man. So if we Z1 minus Z2 plus Z3, ideally the generated image should be smiling man. 그렇죠? Smiling man, right? The smiling woman minus neutral man is going to be just smiling, and neutral man plus smiley is going to be smiling. So in this paper, this again, they show that it is really to that. It's true, right? So this real Z1 minus Z2 and Z3 generate these kinds of images with some kind of perturbation. Then we can check that the generated output is kind of smiling. So this is a very, very important observation. After that, I mean our later part is the interpolating GAN. Nowadays we can interpolate any kind of a GAN model, but this paper was giving the intuition, the understanding of the latent space. 그렇죠? 그래서 이제 이것도 지금 보면 별게 아니지만 이 당시만 해도 GAN이라고 하는 것도 첫 번째였지만 이렇게 레이턴트 스페이스의 어떤 매니플레이션 또는 레이턴트 스페이스 간의 어떤 연관관계를 통해서도 우리가 이제 이 제너레이티드 이미지를 어떻게 우리가 매니플레이트 할 수 있다라는 컨셉을 말해줬다는 측면에서 정말 의미가 있었었죠. So after that, 2017, there was an explosion of GAN to design better training and better generation. So LS GAN, Western GAN, improved Western GAN, progressive GAN, or the style GAN, something like this. So starting from the progressive GAN, nowadays we can generate the images, in fact, in case of the face, but nowadays we can, even human like us, we can't distinguish this is a real or this is a fake. So the generation quality and the fidelity is almost converged. Anyway, the explosion of GAN inspired so many kinds of other applications. For example, image-to-image translation, or the source-to-target domain transfer, for example, like the text-to-images or the sketch-to-images, something like this. In 2019, there was a big GAN. This is the conditional image generation. Unlike the previous method, they just the unconditional image generation. But in this case, to generate these images, they just give condition with a random noise. So this is a dog, glass, or what is that? This is coffee, maybe. 그렇죠? Well, this kind of condition. So this is a conditional generator model, which was a big GAN other loss function. So original GAN paper used just a cross-type therapy loss we discussed previously, but after LS GAN, they used L2 minimization. L2 norm, because it is much stable. And there was a double GAN, 드라간, C간, 인포간, I스간, B간, so many kinds of things. And there was another paper which training method for the GAN do actually converges. They also proposed some regularization technique. Regularization technique. So better regularization technique can help to stabilize your GAN training. So gradient penalty or the con-optive, something like this. So there was another research direction for the stable GAN training. In ICAR 2018, there was a progressive GAN. Idea was very, very simple. They want to disentangle. It's not disentangle. They want to decompose the level of generation. So like this. Okay, so if you want to generate high resolution images, for example, 1000 by 1000, training generator starting from the 1 by 1 to the 1000 1 by 1000 directly, it's going to be really challenged, and it's very sensitive to the learning rate, or it's going to be stuck in local minima very frequently, right? So idea of the progressive GAN was that, okay, let's suppose that there should be the generator looks like this. So starting from the 1 by 1 to the 1000 by 1000, they want to train progressively starting from the coarse layer to the final layer. So first of all, in the first stage of the training, they just train the lower layer, for example, 4 by 4 generator case with one RGB projector, and generate the image. It looks like this. So this kind of the image, 4 by 4 images, just to make a structure of the generated images, and as progressively adding the generator part. Okay, so after first training, in second training, we additionally fill 8 by 8 network to generate 8 by 8 images. And one more technique is the linear crossfade between the 4 by 4 images and 8 by 8 images, right? Because at the beginning, this is going to be noise, 8 by 8 images noise, but 4 by 4 images it's good enough. And as evolving the iteration, we can increase the ratio of these 8 by 8 images to generate these high quality images. So this is a linear crossfade. Anyway, okay, when we train the 8 by 8 images in Discriminator, should be 8 by 8 Discriminator, right? So we can do similar things, right? And by by progressively adding each Discriminator, finally we can train 1 to the 1000 generator with 1000 to the 1 Discriminator network. And after that, we can just feed for 1 by 1 to the 1000 by 1000 image generation, 1000 by 1000 image generation. So this is the progressive generation technique. So this is called ProGAN in ICLR 2018. At the time, there was another direction to use style concept, style code to generate better generator network, which is called style GAN, which was the 2019 paper. But more recently, at the end of today's lecture, we will talk about the style node, which is one of the state of art in the GAN model. But even though this is that's such a recent paper, also based on the style GAN architecture. So to understand this kind of more advanced one, we have to understand the style GAN generator architecture. So let me start. So before that, is there any questions so far? 전반부는 아마 조금 계속 좀 뭐랄까요, 조금 비기닝 관련된 얘기를 좀 했는데 좀 길어져도 1시간 걸렸네요. 혹시 질문 여기까지. 질문? 네. 이 페이지 21쪽. GAN 얘기하는 거구나. What does discriminator contribution converted to 0 over 2 at the end? Does that mean discriminator can't tell real or fake? Right, exactly. So ideally, at the end of the GAN training, the discriminator can't tell or can't discriminate real and fake data. Ideally. 그래서 아이디어라기는 리얼 데이터랑 페이크 데이터를 더 이상 분별할 수 없는 순간까지 간 게 이제 간 컨버지라고 할 수 있겠죠. 그쵸? Any other question? No? All right. So, okay, now to 55. Okay, so after 10-minute break, we will move to the style again, and we will talk about more advanced techniques, 3D aware image generator, for example, like the style SDF or style again, or the graph, something like this. There are so many kinds of advanced techniques. So before that, let's take a 10-minute break. Okay, so let me start in 3, 5. Okay, 우리 10분만 쉬었다가 3시 5분에 다시 보도록 합시다. Right, let's continue. So today we will see the style GAN. So to understand this, we have to understand style transfer first. So what is style transfer? What is style transfer? Style transfer aims to synthesize the images that follow the content of images, right here, and the style of style images. So by manipulating the style or changing the style, the stylized images should preserve the content of the images, but only style information should be changed like this. Or by changing the content images with the same style images, style structures, style information, the content should be same. Content should be edited, right? So in style transfer field, there are so many kinds of technique, but arbitrary style transfer or the ADA-in is one of the most popular technique to solve the style transfer problem. So in StyleGAN, we redesign the generated architecture in a way that exposes the novel ways to control the image synthesis process. So let's think about the StyleGAN. Okay, so first of all, ADA-in defined looks like this. Okay, first of all, before style images and content images, we extract the feature vector and use the ADA-in normalization. What is ADA-in? Okay, let's suppose that this is x vector, x, maybe tensor, right? X then y from content images, style images respectively. And ADA-in is just like the normalization by mean and variance of x and just move to the y feature y distribution by multiplying variance y plus mean y. So this is the ADA-in. So x is here, y is here. So like this. By using this, while preserving the structure of the x feature vector, but we can move the style of the y feature distribution. Then by just using the image decoder, then we can decode these kinds of images. Looks like this. So this is ADA-in module, ADA-in normalization layer. So instead, then they want to use this kind of ADA-in normalization because it was very, very powerful in style transfer field. And image generation is a kind of style transfer. In other words, we can randomly sample the style, then starting from the one fixed content vector, we can generate images that follow these styles. That was the main philosophy. So first of all, rather than using the original images, content images, they want to start from the random noise similar to the GAN, unconstrained GAN, and they want to use the style images to generate the stylized image. It looks like this. So by changing by randomly sample the content vector, we can manipulate the content of images. Looks like this. They follow these style images because this is ADA-in here. One more thing is that every time when we want to image generation, we can't use the external style images, right? So they want to sample the style images from another style noise. There was a question. 정은, is mean standard deviation in ADA-in based on axis of the feature? Right. Right. Axis of feature vector. So, okay. So where is that? Right. So, okay. Ideally, the content feature vector X should be H by W by C. So mean and variance should be computed in C-axis, channel axis, right? Okay. So because this ADA in architecture share the philosophy of the batch normalization, so it just follow the batch normalization. Normalization technique in batch normalization. Okay. So anyway, 여기. So and one more thing is that by randomly sample the style vector with some style mapper. So not a style encoder, style mapper. We can change the style with the same content vector. Looks like this. So it was the two kinds of random variable comparing to the previous method that's starting from the one random variable z. In style GAN, they want to consider the two kinds of random vector, content random vector and style random vector. One more thing is that inspired by the progressive GAN, progressively injecting or progressively generating the images, it's one of the main challenges or one of the key factors in generating the high quality images. So they just followed that idea. So they try to inject the style code for every vector, every layer, looks like this, starting from the 4x4 layer, 8x8 layer, 16x6 layer, to 1000 by 1000 layer. So looks like this. And one more thing is that comparing to the previous architecture, we have two kinds of random variables. So it may be really challenging to find out the mapping function between Z1 and Z2 to the images, comparing to the Z1 to the images. So they just to fix this content vector as a constant value. Then they just want to generate the images by depending on this style relevant random noise. So it's just a constant value. So I mean just to randomly define the constant vector and just randomly sample this style relevant vector. So this is style GAN. So this architecture called synthesized network, and this one is called mapping network or the style network or the style mapping network. So this external style mapping network, this is very simple nowadays, but this one gives many inspiration of modern image generation techniques. So this is our input latent vector from now on. So here. 그래서 이제 한 번 더 설명을 하면은 그냥 기존에 이제 스타일 간 전에 이제 애들은 그냥 어떤 레이턴트 랜덤 벡터 Z 시작해서 그냥 디코딩을 쭉 해가지고 이미지까지 갔는데 그게 아니라 그냥 이 메인 신사이 네트워크는 어떤 그냥 인스턴트 그냥 컨텐트 그냥 컨스턴트 벡터 컨스턴트 텐서 혹은 컨스턴트 벡터 시작해서 쭉 디코딩은 하되 이 랜덤 베리어블을 가지고 스타일 벡터로 만들어서 이 스타일 벡터의 노멀라이제이션을 통해서 생성되는 영상의 어떤 스타일을 결정하자라고 하는 게 이제 어떤 스타일 간의 메인 아이디어였죠. 지금 보면은 어떻게 보면 이게 너무 간단하고 너무 당연해 보이지만 이 연구를 기점으로 이제 생성을 하는 연구들은 거의 다 레이턴트 벡터 매핑 네트워크를 통과시켜서 노멀라이제이션을 통해서 어떤 생성자의 어떤 우리가 매니플레이션을 가해주는 게 가장 효율적인 방법이다라는 것들이 이제 연구가 되기 시작하죠. 그렇죠? One more thing is that this is latent vector Z, and after mapping network, maybe this is just like the MLP module, intermediate latent, which is denoted by W in general. So this intermediate latent vector can be injected to the every layers in generator or the synthesis network. One more thing is that rather than directly use the W intermediate latent vector for hold the layer, they also use the additional affine transformation A, affine transformer A to consider different properties of each level. So this is affine transformer. It's not just transform, it's just like transformation module. One more thing is that they just found that, they just observed that the style has the hierarchy. Style has a hierarchy. The hierarchy of the style can be emerged, can emerge. Looks like this. So, okay. So for example, here. So copying the style corresponding to the course spatial resolution, for example, 4x2 or the 8x8 brings the higher level aspects such as pose, general hairstyle, face shape, eyeglasses, like this. 이렇게 콜스를 바꿔주면 이런 식으로, right? Pose or the general hairstyle or the general structure. And if we manipulate middle level style, style, the middle level style can be manipulated, something like the facial features or the hairstyle, eye shape, looks like this. If we consider the fine style, we just manipulate the tone of the images or the color, something like this. So they just use the different level of style here. Finally, one more thing is that when we generate the multi-level style images, multi-level style to the images, one detailed part like this cannot be adjusted. But in real images, the main detail can be really hard to catch this. So one more thing is that they inject additional noise layer P to consider this kind of the fine detail noises that cannot be captured by the style vector. This is style gap. This style gap. So anyway, this is the left-hand side means the traditional GAN generator, for example, the progressive GAN, and right-hand side means style-based generator. So they just start from the constant vector 4x4 by 512, and there is the noise injection layer and the style mapping layer starting from the random noise Z. Z is from the random Gaussian space. So they are randomly samples during the training and testing time. So this is called style-based generator or the style gap. So the experimental result of style gap was very, very impressive. So this paper was published in CBPR 2019. I was there. The Keras, the Intel guys present this paper in the as an oral paper. So there was so many crowd to watch this presentation. They was just very shocked due to the impressive performance. 그래서 이게 이제 CBPR 2019년도에 기억이 나요. 아직도 제가 이제 요 오랄 세션에 들어가 있었던 기억이 나는데 요 페이퍼가 이제는 뭐 나왔을 때도 인기가 있었긴 했지만 실제 대중들에게 그렇게 알려지지 않았었을 당시에요. 그래서 이제 이 스타일간 저자 케라스 저분이 아마 저분이었을 거예요. 네, 케라스 저분이 발표를 하셨었는데 이제 톡을 하셨었고 그 슬라이드를 제가 많이 가져온 거예요. 그래서 사실 슬라이드 너무 잘 만들었죠. 네, 이제 많은 분들이 이제 그 발표를 보면서 이제 충격을 받았었던 기억이 나요. 뭐 거의 많은 그때만 또 코로나가 없던 시절 이제 정말 많은 사람들이 이제 모여서 이제 그 오랄 발표를 듣는데 이제 너무 충격적이었죠. 이제 간이라고 하는 게 이렇게까지 만들 수 있구나 라는 게. 물론 지금은 훨씬 더 잘 되긴 하지만 그렇죠? Let me show the example. So many style GAN, I mean the many variant of the style GAN after that just use the face images because even though face is also very challenging to model, but it's relatively simple comparing to the other object or the other object class. So there are two kinds of the very popular data set, Cellular HQ or the Flickr face HQ, or just called FFHQ, which is just a face images with varied ages, ethnicity, and background, consistent high quality, something like this. So first of all, in StyleGAN, they show that different style level emerges like this. When we adjust the core style, looks like this, and mid-level style, when fixing other style vectors, other level style vectors, looks like this. Different level of style emerges in the StyleGAN architecture. And they also show that two images, I mean the style of the two kinds of images can be merged to generate the new images. And by adjusting the level of style, I mean the mixing style level, we can adjust the mixing style information. Looks like this. 그래서 스타일 벡터가 섞이는 레벨을 조절해 줌으로써 이제 생성되는 이미지의 스타일 정보들도 우리가 이제 바꿀 수 있다. 그리고 스타일의 레벨도 바꿀 수가 있다. 헤드 포즈를 바꿀 거냐, 아니면 간단한 스타일 정도, 톤 정도만 바꿀 거냐 하는 스타일 레벨까지도 바꿀 수 있다. 라는 것도 보여줬었고요. It's very, very impressive, right? Rather than just using the face images, they also show that other object class or the scene, indoor scene, of course, the quality of the generated images is not so impressive comparing to the face images, but it still looks very, very realistic, real looking images. So this is the fake images. This is the generated images by StyleGAN. So this animation shows the perturbation applied to the images, generated images. Looks like this. Anyway, it was StyleGAN. Are there any questions? Okay, by Yonggi. In StyleGAN, can it be understood as the controlling the context by controlling the depth where the style code is edited? Correct. So, in fact, we don't know exact the level of style because this is just like a byproduct, but we impractically understand that level of the style in terms of the depth. So we partially control the style level in StyleGAN architecture. Okay. Any other question? No? Okay. Then let's move to the conditional image generation. So far we just think of unconditional image generation. So we did not give any condition, but in many cases, we want to give the condition as many kinds of format to the generator. For example, this paper, spade paper. The spade paper, they are coming from the Adobe guys, Adobe. So Adobe that made Photoshop, right? So they want to make a generator that are conditioned on the label map. For example, like this. Okay, we want to generate images, but we want to generate images that follow this structure of the desegmentation map while taking these style images. So for example, this content and this style, then this is generated images. So we want to control the generated images. How can I do that? Maybe among the simplest one is that just take these images label map as an input, and take and apply the convolutional neural network and using the unconditional generator to generate the images. Looks like this. So that's maybe one of the most simplest simply technique. So looks like this. Unconditional decoder with image encoder. Like this. But they found the problem or limitation of this kind of simple approaches. So first of all, segmentation mask contain large uniform regions, something like this, sky or gray, something like this. So when we apply the conventional convolutional module to on this segmentation map, it may become identical or the semantic information is gone. What does it mean? Okay. So let's suppose that this is sky region and this is grass region. Maybe they are annotated by the index 1 or 5. Okay, let's suppose that we apply the convolution module, that we extract the feature vector, and in many convolutional neural network, in most convolutional network, apply the batch normalization to normalize this feature vector. But interestingly, we already know the batch normalization, right? But interestingly, they found that even though they are different feature vector, but they are almost constant vectors. So they, after batch normalization layer, they generate the exactly same output. So all the semantic information is gone. So it becomes identical. So it's not desirable. Why? Because we want to discriminate sky region, grass region to generate the high quality images. So it's not desirable. So that's why the quality of the content image generation is limited. So this paper, Spade paper, try to solve this problem. The Spade, especially adaptive denormalization, was tried to extract especially pairing gamma and beta depending on segmentation mask S. Okay, in conventional batch normalization, this lambda and beta is just learn, 그쵸? Globally learn across the whole spatial resolution. But in Spade, we want to define gamma and beta as bearing the not only channel axis but also spatial axis. So it's going to be tensor, which are depending on segmentation mask S. So they propose this one as a Spade layer. So by just using this Spade layer, comparing to the batch norm layer, we can discriminate the label map as well. So we can high quality images. We can achieve high quality images using this kind of generator containing this Spade layer. So to extract the gamma and beta, they use the additional convolution layer from the segmentation map to extract the gamma and beta tensor, which are element wisely multiplied and added to the original feature vector to normalize the original feature vector, which is a Spade normalization layer. And architecture. So this is a random latent vector. So this is a generator. Rather than using the batch normalization, they apply the Spade normalization that are conditioned on latent, the input segmentation map S here, and they apply to each level, looks like this. And Spade less consisting of Spade normalization ReLU combo, Spade ReLU combo, looks like this with a legit block. So this is detail. Anyway, so this is a Spade less block. Then we start from the latent random noise, and we can generate the images conditioned on this label map. So this is the examples of the conditional image generation. So in this kind of paper, we can control the generated images, at least the structure of the images or spatial layout of the images, by using this kind of segmentation map. 이 segmentation 맵을 이용해서 이제 이렇게 생성되는 이미지의 컬러리를 결정낼 수가 있게 되었다라는 게 스페이드 페이퍼였고요. Nowadays, the direction of the image generation is moved to the 3D aware image generation. 3D aware image generation. Maybe it's going to be the quantum jump from Stylegan to Spade to the 3D aware image generation. Between them, there was so many kinds of paper. Not all image generator, but in image to image translation. So it looks like the quantum jump, but if you're interested in this another papers, please study yourself. 좀 너무 무책임하긴 한데 퀀텀 점프예요. 사실 아까 스타일감부터 스페이드 여기까지 오는 게 이제 스테로이 제너레이션, 오늘 후반부 얘기할 내용들인데 여기까지가 사실 너무 퀀텀 점프긴 해요. 이까지 올까지 너무 많은 얘기들이 있기 때문에. 근데 사실 우리가 이제 그걸 모두 다 다룰 수는 없을 거고, 이제 우리가 오늘은 조금 더 최근 페이퍼들을 다루고 싶어서 이제 바로 좀 퀀텀 점프를 했는데, 중간에 이제 뭐 이미 투 이미 트랜슬레이션이나 를 관심 있는 친구들은 조금 각자 찾아봤으면 좋겠습니다. 됐죠? 그리고 또 좀 많은 페이퍼들이 이제 또 우리 스턴트 페이퍼, 스턴트 프레젠테이션에서 발표될 거니까 같이 봤으면 좋겠어요. Anyway, recent research direction for the image generation is 3D aware image generation. What is 3D aware, or what is 3D awareness image generation? Okay, this is sample from the 3D aware image generator for the same identities but in different poses. Looks like this. Related to the Young's question, in previous condition of previous generator, for example, StyleCam, we cannot control 3D information. For example, like camera pose or the shape or something like this. But in real cases, if the generator aware of the 3D structure, the generator can generate the better quality or the better fidelity images because they already know the 3D structure information. If they did not consider any 3D structure information, they may be limited to generate the multi-view or the multi-pose images because they did not have any camera pose cue. So in stereo image generation aims to separate camera pose or the 3D viewpoint from the identity, such as shape, appearance, only from the unlabeled 3D, unlabeled 2D images. Okay, so if we have the 3D information, this disentangling is going to be really easy, right? Because we already know the 3D information, so we can train the 3D information by discriminative learning technique. But in many cases, we only have the 2D images, so 3D image generation aims at, even though we only have the unlabeled 2D images, I mean the only 2D images, but we want to let the network know the 3D information or the camera pose information. So this is the objective of the 3D aware image generation. So the first paper for this kind of direction is the hologram. The unsupervised learning of the 3D presentation from the natural images, ICCB workshop in 2019. Okay, let's go back to the conditional gap. The conditional gap consists of the generator and discriminator. Generator just take a latent vector z, and if we want to let the 2D generator know the camera pose theta, maybe we can just give the condition. We can give the theta as a condition to the generator, then generate the fake data and discriminate this fake data and real data with the discriminator. But this generator still defined in a 2D space, so they are limited ability to consider the 3D information. So in hologram, they define 3D convolutional module to make our generator aware of 3D information So they define their generator looks like this. Okay, this is the they starting from the 3D random noise and use the 3D convolutional layer and the 3D transformation, explicit 3D transformation by the theta, and because we have to generate the images, they project it to the 2D space and apply the 2D convolution module and generate the 2D fake images and discriminate these fake and real images. This is hologram. If we see this generator in detail, it looks like this. So similarly to the Stelgan, they just start from the constant vector, but this constant vector defined in the 3D tensor space. So not a 4x4 by 512. In this case, 4x4 by 4 by 512. Then apply 3D convolution neural network. And if we have random camera pose theta, then we just 3D transform. Because this is a 3D tensor, we can transform in a 3D manner. So by using the camera pose, we transform the 3D tensor and apply the two more convolution layer and project it to the input images, I mean the 2D images, and apply the 2D convolution layer to generate the images. So during training, by randomly sample the jet and the camera pose, and this using the adversarial technique to train this module, this generator, hologram generator, can be aware of this 3D information. In other words, at testing time, by adjusting this 3D camera pose, we can generate the generated images in a camera pose manner, like this. So by hologram, we can adjust the azimuth or the elevation of the generated images. Looks like this. azimuth는 이쪽 x축으로 바꾸는 거, elevation은 y축으로 바꾸는 거죠. 이런 식으로 3D wave generation을 이제 가능하게 했더라. 아니 홀로간이라는 거죠. After that, the graph, generative radiance field for the 3D aware image synthesis in ECCB 2020 paper was proposed. This paper was based on the neural radiance field. We'll talk about this one, neural radiance field, later. I mean, maybe in our 3D computer vision lecture, but we'll just briefly mention. So my main idea of the graph is looks like this. Okay. So we did not discuss the platonic GAN, but we discussed hologram. So in hologram, we randomly samples from the random noise to the 3D feature vector and process the 3D feature vector explicitly, but this kind of explicit tensor representation is limited. I mean limited to the expressed high quality images, right? This is due to the complexity or the memory, because this is a tensor representation, right? Graph try to overcome this kind of limitation by using implicit 3D representation, which was the radiance field, neural radiance field, and rendered very high quality images, which is the graph. Now, what is graph? So to understand this, you have to know the neural radiance field. This is just free. So if you are interested in more, please see the original paper. And today we just briefly mention. Neural radiance field synthesize an overview of the complex scene by optimizing underlying continuous volumetric scene function, maybe 3D scene function, scene information using sparsely set of the input views. So, let's suppose that this is the continuous volumetric scene function. Then by just sample the position vector, x, y, z, theta, pi. By using the neural network or MLP, we design and we sample RGB and the pi mu죠 맞죠? 아니 시그마 그렇죠? 시그마 as a density value. By just training this MLP neural network, we can represent infinite and continuous 3D space. So in many 3D aware image generator, they just try to use this neural radiance field concept. So the first paper was a graph generative radiance field. They just designed the generator like this. So first of all, similar to the previous unconditional image generator, they consider the latent vector, but they consider the two kinds of latent vector. Latent shape code, which is called the ZS, and latent appearance code, ZA. And because they want to consider the camera pose, so one more latent vector, K is camera. K가 카메라가 아니지. 카메라 맞죠? 카메라 포즈. 그렇죠? K 카메라 포즈 and with a few more parameter. 그렇죠? Xi and V and randomly sample the lay for the neural radiance field and train this G theta function, which is just MLP module, to model the 3D space, color and density of the 3D space. Then use the volume renderer to generate the 2D images, 그렇죠? 2D images. Then this is the generated 2D images. But this kind of whole process is very, very complex and very memory inefficient. During training, they just extract the patches, then discriminate patch discriminator by patch discriminator and train this whole generator. So by doing this, we can generate the high quality images compared to Hologan 홀로간이에요. 홀로간. So this is a graph generator generated images. Because we explicitly control the camera pose, we can camera interpolate or adjusting the rotation or the elevation of the generated images like this. This kind of the output cannot be feasible by the 2D generator, for example, like StyleGAN, but this 3D image generator can do that. One more improved version was the Giraffe. Main idea of Giraffe is to incorporate compositional 3D scene structure into the generative model. So let's suppose that this is the generated images, and in Giraffe, they want to decompose each object and background and learning and testing independently. So this is the Giraffe network architecture, Giraffe concept. So starting from the random shape and appearance code and the camera pose, but they consider the instance-wisely different shape, appearance pose looks like this, as well as background, and composite the information and render to the images. This is the composition 3D scene generation, which was the best paper, which achieved the best paper award at CBPR 2021. Compared to the graph that used the color output, the Giraffe sample the feature output, the feature field. I mean, they just view feature field in the neural radiance field and decode this kind of feature field with a 2D CNN decoder to the input image, to the output image. When you see the detail, we have a latent shape and appearance vector and camera pose, and we have a separate, independent neural representator. Maybe this is just neural network, and generate the feature vector is density, and composing to the single feature representation and just the neural rendering with the 2D decoder, then generate the images. In detail, composition operation, just like the addition with the confidence with the density value for each object, and this neural renderer consisting of the 2D generator, 2D convolution neural network, and they use the simple discriminator to train this kind of the module. This is just output. Control of scene generation by adjusting the object rotation or the camera elevation or appearance and depth translation, horizontal translation, or the subfield translation. We can generate high quality images because this kind of technique is already aware of the 3D information. The real 3D manifold. Then we can adjust the 3D information of the generated images. 이제 이런 러프 뉴럴 레전스 필드라는 개념을 이용해서 이제 우리가 정말 이런 하이 퀄리티 3D 제너레이션까지 할 수 있게 됐더라라는 얘기를 하고 있죠. This kind of paper extended to the Graph HD, which is published in two days ago in arXiv, so which will be presented in future this year. So let's just see the quality of the graph, Giraffe and the Giraffe HD. This paper, the quality improvement is dramatic. So this is network architecture. The main key design of this Graph HD and Giraffe HD is the refinement module. So initial output can be added to the register of the images, and this is the HD quality images in the Giraffe, and this is a Giraffe measured by considering the 3D controllability. Question. 말하다 보니까 너무 어려운 것 같기도 하고. Okay, question to all of you. So, 잠깐만. Okay, so do you already have? So some of you already know some nerve concept, but maybe not. Maybe some of you maybe do not have any knowledge of the nerve or this kind of paper. Okay, so first of all, let's see the question first. I was wondering how we could get the ground truth value for the density of the object in the images. We can't achieve ground truth density function. So in nerve idea, we do not have the ground truth color density, but when we render, when we accumulate this color and density across the ray, looks like this, we can achieve the color value. Then we already know the color value, right? So by just minimizing this color difference, we can backpropagate the loss gradient to this neural network epsilon. Okay. Any other question? 자, 여러분 제가 좀 하다 보니까 조금 어려울 수도 있겠다는 생각이 좀 드는데 어때요? 따라올 만해요? 누구한테 물어볼까? 정은 학생, 혹시 지금까지 제가 오늘 얘기했던 부분에서 혹시 따라올 만한가요?
지금 3D 말씀하시는 건가요?
3D Aware Generation이나 뭐 Neural
음.
Network Field나 이런 것들.
앞 널프 쪽을
음.
그냥 거의 들어만 봤는데, 어, 전반적으로 좀 따라오기가 어려운 것 같습니다.
아, 그쵸,
제가
그쵸.
부족해서 그런 것 같습니다.
맞아, 맞아. 이 너프부터 해야 될 것 같긴 하네. 누구한테 물어볼까 또? 강호 학생. 강호 학생 혹시 이해돼요?
상당히 그 개념적인 것들을 위주로 이해를 하려고 노력하고 있습니다. 네, 디테일은 저도 이제 비전을 주로 하지는 않아서
음.
정확하게는 완전히 따라가고 있지는 못합니다.
이게 참 이게 여기서부터가 이제 문제인데 이 지금 여기서 말한 3D 어웨어를 제너레이터는 사실 3D도 알아야 되고 이제는 2D 간도 알아야 되기 때문에 사실 정말 어려운 파트일 것 같네요. 잘 생각해 보니까. 그래서 잠깐만 우리가 3D 강의가 또 있죠 뒤에. Okay, so I think to fully understand the 3D image generator, you have to know the nerve or the neural network field or something like this. So I think we have to stop here and after 3D computer vision lecture and let's go back. Let's go back to the here. 그렇죠? And let's continue the 3D image generator. 그래서 오늘 스턴트 프레젠테이션 그냥 하되 여기 3D 어웨어 쪽은 우리가 3D 어웨어 제너레이터 쪽은 이 너프까지를 조금 다시 우리가 3D 컴퓨터 비전 파트 공부하고 와서 다시 한번 짚는 게 맞는 것 같아요. 알았죠? 그래서 오늘 스턴트 프레젠테이션 그냥 하겠지만 일단 요거는 우리 다시 돌아와서 그 시간에 다시 보는 걸로 합시다. 그리고 and okay. So one more thing is that interpreting CAM. So it's not a 3D aware generator, so you can understand what I mean in interpreting CAM. So after some presentation, let's go back to this interpreting CAM. Maybe next week. 그렇죠? 이렇게 돌아와서 진행한 걸로 합시다. Okay. Any other question? No? Okay.
그래서 레이 캐스팅이 뭔가요?
레이 캐스팅이 뭔지. 자, 간단히 좀 설명을 드릴게요. 레이 캐스팅을 이해하려면 여기를 이해하는데 여기 너프를 이해해야 되는데 아까 강호 학생 질문과 연관이 되는 건데 결국에 우리가 GT 컬러 덴시티를 알면 그냥 이 MLP를 학습하는 거는 어렵지 않죠. 그렇죠? GT 컬러와 덴시티를 알면. 근데 사실 모르죠. GT 컬러 덴시티 어떻게 알겠어요? 인피니트리 그러니까 인피니트하고 컨티뉴어스 스페이스를 모델링 하고 싶은데 그 각각의 GT를 모르는데 못하는 거죠. 그러니까 하고 싶은 게 뭐냐면 어떠한 레이를 싸서 그 레이 위에 있는 어떤 우리가 샘플링한 점, 이 각각의 점들, 아이고 미안해요. 이 샘플링한 점들의 컬러와 덴시티를 알고 그러면 그 레이 위의 컬러 덴시티를 이렇게 이미지 축, 우리가 알고 있는 뷰포인트의 이미지 축으로 어큐뮬레이션 해보는 거죠. 그러면 레이 캐스팅 한다고 하는데 어큐뮬레이션을 해보면 그게 결국에 이제 렌더링이라고 표현하는데 그 어큐뮬레이션 하면은 이게 결국에 컬러 값이 하나가 나와야 되죠. 그렇죠? 그럼 그 컬러를 우리가 이 뷰에서 컬러를 알고 있으니까 그 컬러와의 디퍼런스를 가지고 결국에 미니마이즈를 하면 우리 백프로파게이션은 각각의 MLP 이 각각의 컬러 덴시티를 만들어낼 때 MLP 쪽으로 백프로가 되니까 MLP가 학습이 된다 라는 컨셉인 거고 이제 레이 캐스팅 결국에 그 레이를 쏴주고 렌더링하는 과정이라고 이해해 주시면 될 것 같아요. 그렇죠? 아마 여기 써 있는 단어를 보고 물어봤을 것 같은데 이거. 그래서 결국에 레이 캐스팅이 뭐예요? 그 레이를 실제 쏴주는 그러니까 어떤 레이를 쏠 건가 우리가 를 결정해 주는 과정을 보면 돼요. 알겠죠?
네, 감사합니다.
오케이. 나는 이런 학기도 일제 영향되고 있는 바가 여쭤보고 있는 너무너무 사실 상성 기술은 사실 중요하죠. 그러니까 사실 엄밀히 얘기하면은 생성 기술 자체가 딱 어떤 엔드 프로덕트로 쓰인다기보다는 사실 간이라고 하는 연구, 제가 왜 제너레이티브 모델에서 간을 공부해야 되나 했던 이유가 제너레이터 연구, 사실 처음에 이런 제너레이션 연구들은 거의 for fun에 가까웠어요. 그냥 조금 재미를 위해서 이렇게 얼굴도 나오네? 라는 거에 가까웠지만 그 어드버서리얼 컨셉 그리고 어드버서리얼 어떤 테크닉들은 사실 정말 많은 태스크들에서 사실 활용이 되죠. 예를 들어서 뭐 이미지 투 이미지 트랜슬레이션 또 도메인 어댑테이션 또는 뭐 정말 많은 태스크들에서 이제는 저런 디스트리뷰션을 맞춰준다는 컨셉, 모델 테크닉이 많이 사용될 수 있고 실제 그런 데 사용이 되고 있고요. 그리고 굳이 엔드 프로젝트를 생각해 보자고 하면 뭐 딥페이크 기술들, 그렇죠? 또는 뭐 AI 아나운서 같은 것들이 사실 거의 다이렉트하게 사용될 수 있는 어플리케이션이었죠. 그렇죠? 준혁, perhaps I know you're not covering the diffusion model in this narrative lecture, but I was just curious on your thoughts on new SOTA model. As you mentioned earlier, score-based model tends to be hot topics in the generative model. I was right. I think diffusion model is much more powerful method to generate your sampled data. Even though the theory is very, very tough and theory is very, very, how to say, heavy, but I think we have to move GAN to the diffusion model in many applications. So maybe in this lecture we can't deal with, we can't discuss diffusion model, maybe, because we have so many kinds of topic we discuss, but if possible, maybe at the end of this lecture, at the end of this course, I will make some session to discuss the diffusion model. So to conclude, to summarize, we have to know that we have to move GAN to the diffusion model, I think. Okay. Right. So now let's move to the student presentation. Okay. So today we will see some of the student presentation. Okay, here. So we have 6 papers, and 5 of them is paper with code review. So it's going to be really maybe more than 1 hour. 그렇죠? 1시간 넘게 하죠. 그러니까 오늘은 today we will see 2 of them. Okay, 2 of them. So this paper representing scene as a compositional generative neural network, which is the graph, giraffe, and the style nerd. So 2 paper, and remaining paper we will see this remaining paper in the next week. Okay, so so let's start. The first paper is the giraffe by Byung.
Yeah. Yes.
Okay, so please start.
You. You
okay.
are disabled.
Okay, so you can share now.
Hello everyone. I hope you guys already see my screen. And Can you hear me?
Yes, and please remember that you only have the 25 minutes, so please.
Yes, thank you.
Okay.
So hello everyone, I'm Ching from Electrical Engineering Department. Today I'm going to present the graph representing scenes at a compositional generative neural feature field. The work from Michael from the University of Tübingen, I guess. Most of us know about deep generative model, which is have the great potential with just a random vector from a latent code, and the model we can have the really realistic image. But it's not all we want. We may want to control over the image generation process, which is for example, if we take a picture and we want to like Photoshop it, make it better, so we know what the direction we want to have. So to understand the paper that professor already covered, the background idea about the scene representation from the neural radiant field, which is the ideas of that paper. Just they have we already have, it's just the paper that conceptualize how we present the field or the field. So move on from that, we have the paper graph, which is the combination. It's this a combination of the previous paper, the neuron radiant field and generative model to generate the better image. So the graph different from the paper. From the main idea of this is the graph and the node represent the entire scene at a single radiant field, but the graph employ the compositional nature of the scene at the model, every object and the background at the separate feature field. So in the paper, they call it the separate feature field, which is just the term for the radiant field, but for multiple objects. With the they may do it with the shape or the appearance of the code. And with the addition to it, they have the applied transformation associated with each object, which I will go to more detail later. So for each of the object, they may do the scaling, translation, or rotation the matrix. So they also do it with the object or the scene space. What is that? Professor already explained a little bit about that, but the main idea is in the paper, in the code, it's not a picture in here, but they play the car in here, so we can understand what kind of aspect they want to focus on. So let's say we have a picture of a car, and with the shape appearance, we have the pose of it. In here, they can scale the object to smaller, or they can change the shape and appearance. We have the vector that represent the position of the object in the picture. And so unlike the previous paper that they have only have the volume rendering, so in the graph they do it with in the low dimension, so it can save a lot of resources like time and computational resources. And then after they have the volume rendering from the low dimension, so they have the neuron rendering to have the higher resolution image. So this is the main, these two are the main contribution of the work. So there are some example, the good result from the paper. So we already know about 2D GAN base. So they perform the 2D GAN space and have the picture look like this. And this is the 3D waveform graph. So we can see the difference between the 2D and 3Ds in here is because the 2D, if we move the object, then one other object may be affected by the third object. But with the graph, when we move the rectangle around, the other objects still remain. So they claim that with their work, the object is completely separate or independent from the background. Also, the work can moving the object around or adding in first they're adding more object to the picture, and they can move the object around, which is yeah, people impressive by that. Me too. I think it's awesome. So this is the so there are a couple of keynote that we may want to remember about the work. So the work leveraging the knowledge about 3D nature of the real work, which is the camera pose or stuff like that, to explicitly control the position, shape, and appearance of the object. So in the testing time, we know what kind of movement we want, so we can tell the model that we want to move to the left or right. So with that vector, we have the picture, the object moving around. And other main contribution of the works is without the strong supervision from this any supervision, the screen is disentanglement. From that means the object are independent from the background and other object, and the shape of the object and the appearance, position, and rotation in the scene can be explicitly controlled. And the scene generalize beyond the training data. That means they can increase the translation range or the number of the object. So in the training data set, we may have only one car in the picture, but based on their work, they can add more car to the picture. So those data that doesn't include in the training data set. So this is the overview of the work. Now I will move to the coding review. If you guys have any questions, feel free to ask. So, sorry, I don't know how to train the view here. So now I will go to the code review. So firstly, this is the code from the author. If we just download the code and run the training, we can run the models. And if we run the rendering file, we can have the the cars that changing the scene look like this or like this. This is the translation from the paper. In here the cars are moving around. So this is the overview of the code. Now I'm going to go to more detail about the model. We can firstly we can download the data set, and we can define the graph module. So in the graph module, as usual, we have the discriminator, the generator, and the generator test. In here, the generator and the generator test is identical, but they split it to that. So in the training and validation, they can fix the model more easily. So we're going to define the discriminator and the generator. I will talk about this later, and I'm going to talk a little bit about the training step. So for each training step or iteration, firstly, we're going to fix the discriminator to learn the generator, and vice versa. Fix the generator to learn the discriminator. So for each training step here, firstly, we train the generator, and then we train the discriminator later. For the generator, we will have the latent code or latent vector that generated by the function called, they have this function. So I have a note in here that the input for the generator is a lit4 random vector, which is the latent code, like in the normal GAN. In normal GAN, we have just one latent code, but in this graph, we will have 3 other more, which is about the posing, camera transformation, or the background rotation. So when we obtained the vector from the random field, and we can fit them to the module, generator module, and then compute the loss function from the discriminator. And in here, we treat the face image as 1. And then we train the discriminator, which is still easy like other generative model that have the real picture in here. And then in here, they also compute a loss between the real and the face image. So I'm going to talk a little bit about the 4 random vector that they fed into the generative model. I'm not going to go to detail how they have it, but here are some examples that I printed out so we can have the vague idea of what it is. For the latent code, we have a couple of random vector, and we have the random camera, which is the matrix look like this. It's not exactly random, but it's sampling from the random vector, random field, which is the Gaussian. And also we have the random translation, look like this. So and then now I'm going to talk about the discriminator and the generative model. So the discriminator can be any, in here they have done simple one, or maybe you can use the ResNet or other network, it's no matter. And then we define the generator. We have 4 input to the generator, and in the generator we have 4 main components, that the decoder, the background generator, and the bounding box generator, the neuron renderer. So we define 8 of them. This look like this. Then we define the bounding box generator, neuron renderer. So for now, we have all the component of the network. Then when we fed the four random vector to the generative model, we will have all the component, and then when we have all the component, we're gonna fed it into the neuron renderer, and we will have the output. So this is the this is my presentation about the coding review. That's it. If anyone have any question, feel free to ask.
Thank you very much. And question for this paper?
Yes.
It's not my question. I just asked a question from the audience.
Yes.
질문 있는 친구들? 네, question? No? Okay, thank you very much. And so this draft code and this Jupyter notebook is already uploaded in our Google Sheet.
Yes.
So please check that if you want to see detail. Okay, thank you very much. And let's move to the next presentation. Next presentation is presentation is style-based 3D aware generator for high resolution image synthesis by Jae-hoon. Please start.
Can you hear my voice?
Yes.
I'll start my hello, my name is Jae-hoon Ko. I am working in Professor SeungryongKim's Computer Vision Laboratory, and today I will present a Steiner paper. So I brought this slide for maybe someone does not know about the NERF. So I'll briefly explain about this. NERF is basically this multi-layer MLP layers, and this layer becomes overfitted to these 3D scenes, and the method is to predict the density and color of each of the 3D location, and input becomes the 3D location and view direction. And after that, if we can accumulate the every 3D points through the one ray. That ray becomes 1 pixel point, and that becomes the color RGB color value of that pixel. And we have the ground truth image to compare that pixel. So NERF is yes, NERF is like works like that. And as the Professor Kim already said about the generative models, the NERF, many people exploit NERF to generative models, but they have two major limitations, which is they are hard to get high resolution image because it is very inefficient compared to 2D GANs. The author said it is up to 1,000 computational cost, and Also, they are weak at 3D consistency. As you can see from this image and GIF image, the 3D shape should stay still, but as the camera point changes, the shape and color changes a little bit. So Stylenov's approach and the main contribution is to get rid of these two major limitations. They tried to generate high resolution images and also in efficient way. And also they try to keep the 3D consistency. So the first approach is to use the upsampling rate. Oh, sorry, this should be reversed, but I missed this. First approach is to use the 2D upsampling layers, because if we sample all of the pixels in high resolution image, the computational cost increases very extremely. So they just render the volume. They just volume rendered in low resolution feature maps, and they just upsample the feature map to high resolution images. This is very this was actually first presented in Giraffe, but they used their novel upsampling layers to keep the image more consistent in 3D. And the model structure looks like this. Every blocks of this in this image came from the StyleGAN structure. This is StyleGAN 2 structure. They used mapping network to extract the W and gave every W to the comb layers to modulation and demodulation process. And also this comes to the upsampling layers. This is upsampling layers to get high resolution RGB layers. So this is another mathematical terms in Stylenov, but this is basically the same as presented in NERF terms. But the only thing different is they use upsampling layers. So they get the efficient they get high resolution imaging by efficiently by upsampling layer. But so another main point of the paper was keeping 3D consistency. So this means the same point in 3D space should represent the same color and density. So they presented novel upsampling layers. In Giraffe, they used just upcomb layers, 2 upcomb layers, but they used pixel shuffle layer and another. This was comb layer and this was this was another comb layer, but they said that using this both comb layer and pixel shuffle helps models to keep 3D consistency. So this was presented in Stylenov paper. They said this pixel shuffle makes to stick the texture sticks to same pixel location. As you can see this image, the color of a white bird should stay in the same area, but same 3D space, but they stick in the 2D space. So this was pointed by the author, and also this was another regularization term to keep the consistency. The upcomb layer can degrade the quality of 3D consistency because it is just approximation of the nerve. So they used original nerve to patch sample the ray, and this becomes the regularization to this. This is Steinhoff, original Steinhoff, and this is original just nerve. They use these patchy images to keep the 3D consistency because this is more consistent in 3D. And another thing is the original nerve.
Okay, so
The
please remember
original-
that we have a 5 minute for the paper presentation, so please, okay, finish within maybe 2 or 3 minutes. Okay.
So another thing is the nerve should nerve is basically the input direction changes the color value because it is it should be different in the variation of light reflectance, but this can degrade the 3D consistency because the model can compromise to the realistic images. So they compromise the quality both between the quality and 3D consistency like this. So the hair direction should stay in this direction, but they compromise to move to here because this is more realistic in the GAN-based models. And this is another term, but they just said this was only optional things, so I will skip this. And this is the experiment of the Steinhoff paper. This was previous GAN-based 3D mobile view synthesis papers. The Steinhoff is presenting very good very good quality. Also, they can change in styles and also the camera position very well. So this is end of my presentation, and I will continue on code explanation.
Okay, thank you very much. And Jaewoon, there was two questions by Jeongin and Youngin. Please answer that.
John, so the pixel shuffle John, so I think the author said that just bilinear upsampling makes it is similar to the thing on here. They compromise on the quality. I think they said pixel shuffle makes that compromising more. They more easily compromise on this condition, bilinear upsampling. So I think they mix those two things. And
Okay, but I'm pretty curious about the concept of why using this pixel shuffle or bilinear upsampling is good. I don't get the concept of why.
혹시 교수님 한글로 해도 될까요?
네, 뭐, 네, 그렇게 해봅시다. 네.
감사합니다. 그러니까 픽셀 셔플을 왜 픽셀 셔플과 왜 바이리니얼 업샘플링을 왜 썼는지가 궁금하다고 하신 건가요?
네네네. 그게 이제 3D 컨시스턴시를 보존을 한다라고 하시는 것 같은데 약간 그 연결고리가 뭔가 직관적으로 와닿지가 않는 것 같아서 좀 여쭤보고 싶어요.
그러니까 얘네를 써서 그런 게 아니라 사실 업샘플링을 해서 하이 레졸루션으로 올려야 되는데 그냥 바이리니얼 업샘플링은 그냥 스타일겐 2에서 사용됐었는데 요거를 쓰니까 그 3D 컨시스턴시가 낮아졌고 걔네를 좀 보강을 해주기 위해서 픽셀 셔플이 그런 컴프로마이징에 좀 둔감한 경향이 있어서 두 개를 섞었었다라고 저는 이해를 했어요.
네, 감사합니다. 네, 그리고 그 윗슬라이드에서 이제 풀그라운드랑 백그라운드랑 나누던데 그거를 중간에 어떻게 나누는지가 조금 감이 안 잡혔거든요.
그러니까 포그라운드랑 백그라운드를 따로 다른 너프 네트워크에 넣어버려요. 그래서 그 따로 나온 덴시티들이 있으니까 걔네들을 이제 같은 공간에다가 배치를 시켜봐요.
풀그라운드랑 백그라운드는 그 약간 프리디파인드 된 건가요? 그러니까 라벨이 있어야 되는 거인 건가요?
라벨은 필요가 없고 약간 랜덤 샘플 하는 느낌인데 카메라의 포인트에 따라서 백그라운드의 위치가 정해지게 되거든요. 그리고 그 레이 샘플 하는 포인트들도 다 정해지기 때문에 걔네들에 따라서 네.
네, 알겠습니다. 네, 감사합니다.
영은님 in equation이라는 게 몇 번째 페이지였나요?
페이지 6인 것 같아요. 네.
이것도 아까 말씀드린 거랑 비슷한 것 같은데 아까 그 픽셀 셔플이 그냥 바이리니얼 업샘플링만 사용하는 것보다 혼합해서 사용하는 게 좀 더 컨시스턴시를 강화하는 데 도움을 준다 그런 식으로 이해를 리핏은 이제 그 채널 와이즈로 이제 좀 이게 컴브레이어들이 이렇게 있어가지고 얘네는 컴브레이어 붙여서 나온 아웃풋들이고 얘네들은 그냥 채널로 더 그냥 리핏만 시켜요. 그래가지고 채널로 더 길게 붙여놓은 다음에 각각을 붙여서 픽셀 셔플을 하는 걸로 있습니다.
저 리핏이 채널별로 붙인다는 게 혹시 어떤 뜻인가요?
채널 와이즈로 그쪽으로 컨캣을 시켜가지고
피처를 컨캣한다는 말인가요? 그럼 중간 레이어의 피처를 컨캣한다는 뜻인가요? 마지막에 피처 저 X랑 4의 의미가 잘 이해가 안 가서요.
X 자체가 피처 맵이고 그걸 4번 리핏 해가지고 채널 쪽으로 컨캣 시킨다고 이해했습니다.
그리고 파이 세타는 그냥
얘는
피처...
이제 네, 얘도 컴블레이어인데 논문에선 2MLP 레이어라고 되어 있었는데 코드에서 보니까 컴브 레이어더라고요. 아마 1 곱하기 1 컴브 레이어여서 그렇게.
아, 네, 감사합니다.
Okay. Any other question? No? Okay, I think we have 10 more minutes, right? So I think you need more time to explain your code. So I think you have to present your code review again next week, maybe. So yeah, it's okay to you? It's okay, 재훈?
It's okay.
Okay, so that's it. Other question on today's lectures or the generative model, something like this? No? Okay, so that's it. So this is end of today's lecture. So today we just to see what generative model is and some advanced GAN model, scale GAN, spade, or the 3D aware generator. And we just talk about giraffe and the style null, right? So next week we will see the remaining the papers, style SDF, style clip, score-based generative modeling, which is maybe 그 diffusion model, or adversarial NAS, the adversarial neural architecture search for the GAN. And we will finish the interpreting GAN about the how to understand your generator next week. Right? Okay, that's it. So thank you very much and thank you this week and see you next week. 자, 여러분 오늘도 너무 수고 많으셨고요. 우리는 이제 다음 주에 다시 한번 보도록 합시다. 수고 많으셨습니다.